Here's an interesting question which combines geometric progressions with trigonometry. Okay, and this is a question that was given to students who sat the IB high-level maths exam. Okay, and if you'd like to see anything similar to this, maybe you'd like to see some difficult IB questions, let me know in the comments and we'll sort it out. Right, so in this question we're given the first three terms of a geometric sequence, okay, and those three terms are as follows. So I'm going to call the terms A1, A2, and A3. So we have that A1 is root 2 cosine x, right? By the way, don't make the confusion of putting the cosine under the square root, okay? That's strictly the square root of 2 that's multiplied by cosine x, which is not under the square root. And then we have a2, which is sine of 2x. And then we have a3, which is 2 root 2, and then sine squared of x cosine of x. So it looks like it's getting more and more complicated the longer we travel along this geometric sequence, okay? The other thing that we're told, which is pretty important, is that x is between minus pi over 2 and pi over 2, okay? So if you think about it, if you think about the unit circle, this means that we are either in the fourth or in the first quadrants. Okay, and this is something that we're going to use later. But for now, we're going to start with part A, which is related to finding the common ratio. Now, even if the question did not ask you explicitly to find the common ratio, you should still do it. Okay, whenever you have a geometric sequence, it's a really good idea to find what the common ratio is. So let's do that. We have, let's take here part A. So the common ratio, let's call it Q, is equal to the ratio of two consecutive terms. So it's going to be, let's say, A2 over A1. You could do it with A3 over A2 if you want, but I'll do it A2 over A1. So A2 was sine of 2x, and A1 is root 2 cos x. Okay, so let's try to use some trigonometry to simplify this a bit. So sine of 2x is the same as 2 sine x cos x. And we're going to leave the denominator as it is. And you can see that there's a simplification here. The cosines cancel out. So the ratio is going to be, so 2 over root 2 is root 2, and this is sine x. So that's it. Okay, so Q, the common ratio is root 2 sine x. And just to check this, we're going to try to obtain the third term from the second term by multiplying the second term with this. Okay, so A2, we said it's equal to root 2, the first term. So the second term is sine 2x. Okay, which is, of course, the same as 2 sine x cos x. Now, if this is indeed a geometric sequence, then we must have A3 equals A2 multiplied by Q, which is 2 sine x cos x, right? That's A2, times Q, which is root 2 sine x. And this is going to be 2 root 2, right? I'm just multiplying the 2 and the root 2. And then we have sine squared x cos x. Okay? Which is exactly this. Is the third term that we're given in the question, so we can conclude for certain that this is the common ratio. Right, so for part B, we're asked to find what is x, or what can x be, what set of values does x have, for which this geometric series converges. Okay, so let's try to write this geometric series. So we've got root 2 cos x plus, so this was the first term, and then we have plus sine of 2x, and then we have plus the third term, which is 2 root 2, and then we have sine squared x cosine x, plus, and so on. So remember, this is an infinite series, okay? Now, let's try to remind ourselves what the form, or what the formula for the sum of an infinite sequence is. Okay, so the sum is given as follows. So we have the first term plus the second term, which is just the first term times q, plus the first term times q squared, plus and so on. And if you call the sum Sn, this will be a1 q to the power n minus 1. Okay, so we can now factorize a1, and this will be just 1 plus q squared, and so on, plus q to the n minus 1. Right, so this will then be q to the power n minus 1 over q minus 1. So this is something that you'll probably find in the formula book. Okay, you'll find that this is actually equal to this, basically. Okay, so that's the general expression for the sum for the infinite series. So in our case, we have the following. So the sum of the first n terms is going to be equal to the first term, which is root 2 cos x. So let's say root 2 cosine x times, and then we have 1 plus q squared plus all the way to q to the power n minus 1. And for this to converge, right, so this is equal to this, and for this to converge, we must have this term, we must have q between 1 and minus 1. Okay, that's the condition of convergence of this infinite sum, basically. So as n becomes infinite, for this to not become, for the sum to not become infinite, we must have q between minus 1 and 1, okay, without minus 1 and 1. So let's remember what q is. So q was root 2 sine x. So we have root 2 sine x, and this should be between 1 and minus 1. Okay, so sine x is going to be between 1 over root 2, which is root 2 over 2, and is going to be greater than minus root 2 over 2. Okay, so finally we have that the sine of x should be between root 2 over 2 and minus root 2 over 2. So where should x be in that case? So if you remember, our x is between minus pi over 2 and pi over 2. Okay, so let's try to draw the unit circle to understand this a bit better. So let's split this up in 4 quadrants, and we know that we're supposed to be, well, somewhere here. Okay, those are the this is the first quadrant and this is the fourth quadrant. And sine of x has to be between root 2 over 2 and minus root 2 over 2. In other words, what we must have is that x should be between arc sine of root 2 over 2 and minus arc sine of root 2 over 2. Okay? Or arc sine of minus root 2 over 2 is the same thing in this case, because arc sine is an odd function. So this is telling us that x should be between minus pi over 4 and pi over 4. Okay, so the correct range of x is going to be this one. All right, so any x in this range except the ends of the interval work. Okay, so that's the end of part B now. So hopefully we got 4 points so far. And for part C, we are using this new thing that the question tells us. So let's start part C here. So we're told that x is going to be equal to the arcsine of 1 over 2 root 2. Arcsine of 1 over 2 root 2. And also we're told that now x is between 0 and pi over 2. Okay, so this arcsine I like to rewrite it because I don't like square roots in the denominator. So I'm going to use square root of 2 over 4. Okay? And we don't actually have an exact value for it, so we're going to carry it as it is. And the question they ask is, show that the sum to infinity of this series is the square root of 7. Okay? So, in other words, we are going to take this and we're going to input it here, and we're going to show that that sum is going to be square root of 7. Okay? So let's see what we then get. First of all, we have the fact that the sum is a1 times q to the power n minus 1 over q minus 1. This. Okay? So the first element in this infinite series is root 2 cosine x, like this, and then the ratio is going to be what we found in part A, which is root 2 sine x. So we have root 2 sine x, and this is going to be to the power n minus 1 over root 2 sine x minus 1. Okay, so if this converges, essentially this term will go to 0. Okay, so in that case, this is what this will turn into. So the sum will approach, as n will approach, root 2 cos x times 1 over 1 minus root 2 sine x. Okay, so I multiplied with minus 1 on the top and on the bottom of the fraction. So we know what x is in terms of the arc sine of root 2 over 4. So let's actually use that. Now, this here is going to be easier to deal with. So sine x is going to be sine of arc sine of root 2 over 4, which is just going to be root 2 over 4. So that's the function of the inverse of x, basically. So that's just equal to root 2 over 4. Now, the problematic part is going to be the cosine, okay? Because this cosine is going to be the cosine of an arc sine. So we don't yet know how to deal with that, but we'll see in a second. So this is cosine of arc sine of root 2 over 4, like this. Right. And for this, to find out a closed form expression for the cosine of arcsine, we're going to use the fundamental theorem of trigonometry. In other words, we know that cosine squared of theta plus sine squared of theta is equal to 1. Okay? So let's replace theta with the arcsine of root 2 over 4. So we have the cosine squared of arcsine of root 2 over 4 plus, and then we have sine of arc, or sine squared of arc sine root 2 over 4 is going to be equal to 1. Okay, and what we're trying to find is essentially this side, and we know this is essentially sine of arc sine of root 2 over 4 and then squared. So sine of arc sine of root 2 over 4, just make this look a bit better. So this is root 2 over 4 squared. So this is 2 over 16. Which means that the first term, the one that we're interested in, the cosine squared of arc sine of root 2 over 4, is going to equal 1 minus, and then we have 2 over 16, which is 14 over 16. So the cosine of arcsine of root 2 over 4, okay, we're just going to take the square root of the right hand side, and that's going to be the square root of 14 over 4. Now remember, this technically could be plus or minus, but because we're dealing with the first or the fourth quadrants, the cosine is always positive in those quadrants, right? So this is going to be plus because we're somewhere in that, well, even more than that, we're somewhere in this yellow region, basically, okay, which is the first or the fourth um, quadrant. So that's where the cosine is always positive. So we found cosine of arcsine of root 2 over 4 is equal to this. So that's good. We can now finish the question by finding the limit. So the sum Sn will go towards root 2 cosine of that. So root 2, and then we have cosine of x, but x is this. And we just found what cosine of arcsine of root over 4 is. So it's root 14 over 4 multiplied with 1 over, and then we have 1 minus root 2 times root 2 over 4. So we have root 2, and then we discussed earlier that sine x is root 2 over 4. So root 2 over 4. Okay, so this will give us the following. So root 2 times root 14, you can actually take out a root 2 from here, because this is equal to root 2 times root 7. And if you multiply this by this, you just get 2. So this is going to be 2 root 7 over 4 multiplied by 1 over 1 minus, and this is 2 over 4, right, which is a half. So this will be root 7 over 2 times, and this is going to be 1 over 1 half, which is 2. So this cancel, those two cancel out, so the final result is going to be root 7, which is what the question wanted us to show, right? So we're given this, and then using this by plugging this in here, we showed that the sum, the infinite sum, is root 7. And that's the end of the question.